Okay, welcome everyone. Let's get started in just a minute here. And we just, I guess, a couple of announcements before we begin. There is a quiz on Thursday, right? So just to be Chapter 6 type stuff, okay? All right. And that's about it for the announcements, I suppose. I guess the other announcement is that regarding homework, you saw that I sent out the email over the weekend. Said the part 2 of Chapter 6 homework is due on Saturday, and another assignment will be going up later tonight or tomorrow on Chapter 7. Okay, and you'll have a week to do that. Oh, thank you. And so the other announcement is that the STEM speaker series starts tomorrow, and so now would be a good time to go and do attend some of the speaker series. There will be some food, I think, free food, and so stop by, get some dinner, hear a good inspiring talk, and pick up some extra credit for the class. Well, it's sort of required extra credit, kind of, right? If you look back at the syllabus, it's like you have to do it, but you get credit towards your final exam. Okay, so let's begin Chapter 7. And what we're doing this evening is looking at plastic deformation and what goes on kind of at the atomic and crystalline levels when you plastically deform a material. All right, so we'll recall that plastic deformation is permanent. It corresponds to the breaking of bonds. Now we've seen this already. We saw that usually when plastic deformation occurs, an entire plane of atoms slips past other planes of atoms. So it's a net movement of large numbers of molecules, and you in fact get a change in shape, as we saw in the tensile test step where the area actually reduces on the way towards fracture. The way that this happens is as we discussed, was plane slip, and when an entire dislocation moves. All right, so really, kind of, we're going to be looking at this concept through this module, is the motion of a dislocation. Remember what a dislocation is? It's an irregularity in the crystal structure, right? So we'll see that on the next few slides in a second. But to move a dislocation, these irregularities, you have to incrementally break bonds and then reform new bonds. So here's a picture of what that might look like. And you can actually kind of look at it sort of similar to a caterpillar moving. If we have a dislocation at this point here, we can look at each phase of the motion of a dislocation as propagating through towards the right. If there's a force that's pushing towards the left and towards the right, and you have kind of a shear force applied to this sample, then this dislocation is going to move towards the right. Now, that doesn't mean that the actual atoms in blue move, and these are the same atoms propagating from phase 1 to phase 2, phase 3, and so on. They're not the atoms in blue aren't the ones actually moving. What's really happening is that there's a gentle push of the top plane of atoms here, this top plane, where these blue atoms are going to now form bonds with this guy, and basically this will shove the dislocation. New bonds will be broken, and new bonds will be formed, and the new dislocation shows up further towards the right. But this dislocation is now the atoms that used to be over in this point here. So if you look at this piece here, these dislocation atoms used to be right here. And before, they were in a perfect crystal structure, but through the applied shear stress on the outside is actually influencing the dislocation to kind of propagate towards the right. All right, so what's happening here? Bonds are breaking and new bonds are forming. And in fact, by the time you get all the way out to the end, you'll notice that the dislocations are just sitting at the end here. And so you have, in fact, sort of a perfect crystalline material in the center of the body. So we can view this with Goldie the caterpillar, which was first rolled out by UC Davis in 1979. They put this cartoon together that a caterpillar, and we'll call her Goldie, moves in a way similar to dislocation motion. So if we tried to take Goldie and pull her by her little antennae from across the ground like this, she's going to get really sort of angry, you know, right? Because it hurts, and really all of her bonds are stretching and holding her back, right? So the idea is that it's difficult to break all the bonds at once, right? Something that's much more palatable for Goldie and easier from an energy perspective is to give her a kick here. Sort of, imagine if we just pushed her behind up a little bit, that would scoot in this way, that would scoot her body in that way, and then the only bond you have to break is this one right here. You break that bond and now it's free, right? So instead of breaking 1, 2, 3, 4, 5 bonds all at once, which takes a lot of energy, you're only breaking one bond at a time. And the bond then, or the sample then propagates. And we can view that like this this dislocation mechanism here, showing this this edge dislocation propagating through the crystal lattice. Okay. So let's look at something called dislocation density, and to give you some definitions. This is the total dislocation length per, well, there's two ways to define it. One is the total dislocation length per unit volume. So the units are millimeters of dislocations over cubic millimeters. So if you're looking inside of a cubic area or any three-dimensional volume, and you see that there are a number of dislocations, and one is this long, another one is this long, the L2 is this long, and each dislocation has a certain length. If you add them all up and divide by the volume, so it's the total dislocation length per unit volume, that's what gives you the dislocation density. And another way to define it is by analyzing the number of dislocations that intersect per unit area. So basically, if you just count all the dislocations, if we were going to count these, and this is 1, 2, 3, 4, 5, and so on, and counted up all the dislocations that we can see in this extra micrograph, we take that number of dislocations, capital N, and divide it by the total square root of the area. And when you do that, that gives you the dislocation density per unit area. So two ways of defining it. Incidentally, the micrograph was formed by etching the sample, and that's a chemical process in which an acidic solution is passed over the surface of the material and eats away the outer atomic layers, the outer atoms. And what happens then is that, remember that dislocations at the once you get down towards where they are, you'll see a pit where the dislocation is, because there's a discrepancy there's an irregularity in the crystal structure at that point. So these small little pits show up on the micrograph, on the etched sample. What are some of the sources of these dislocations? One is solidification. So when a material, like let's say a metal, is entirely molten, it's liquid. The atoms are just moving around in all sorts of ways and directions, and you begin to solidify the material as you begin to cool it, and some of the atoms or molecules start to lock into certain positions, and they'll do their best to form a crystal structure, but there may be some areas in which a perfect crystal structure was not formed. And there could be voids, vacancies, where there should be an atom at a particular lattice site and there isn't, or there could be whole planes of atoms that are kind of shifted away, like a half plane of atoms, like an edge dislocation. Another way that we're going to see, questions? Yes?
In terms of like when solid, or when the liquid becomes solid, sometimes it's not completely solid, there are little bubbles in it. Would that also be considered a dislocation?
So the question was, sometimes when a liquid is becoming a solid, sometimes there are still bubbles in it. Thinking of ice cubes, maybe?
Ice cubes, I think
some metals have some bubbles in them. And would those be considered dislocations? And if you're talking about when the sample is completely cooled and solidified, right? And there are just sort of some air, let's say air bubbles in there. Yes, those are dislocations, or those are irregularities also, which are dislocations in the sample. Yes. Good question. So solidification is one of the mechanisms that can develop these dislocations. Another method is through plastic deformation. As we'll see soon, it turns out that when you plastically deform a material, you're moving entire planes of atoms, and that's creating new dislocations. Yeah? Fair enough, right? Seems reasonable. If plastic deformation corresponds to atoms completely migrating, they might migrate into a position that is not part of a perfect crystal lattice where their final destination is, these atoms. And so, so that's a way to induce it. Another one that we'll see is, especially when we get towards chapter 9, is thermal stresses and thermal processing. Okay, so when you plastically deform a sample, some of the energy, a lot of the energy goes into heat. In fact, most of the energy is dissipated as heat. As bonds are broken, atoms slide past one another. Most of the energy is released as heat. And some of the energy, about 5%, let's say, is stored in the bent or deformed bonds, the irregularities in the crystal. And we call this strain energy. And that strain energy is schematically shown on this picture, on this top-down view of a crystal structure or crystal lattice that has an extra half plane of atoms inside of there, which is an edge dislocation. And we note that that extra half plane has, at this point here, if we were to draw a line in between where the half plane is and where the half plane ends, we note that the radius between atoms is less than the equilibrium spacing R naught. So what you remember that when that occurs, remember if you look at the energy, this has a sort of picture like this, right, where R naught is the minimum energy. And if you're at a position less than that, you actually have some stored energy in those bonds. And those bonds, that energy can be, that's stored in the sample, basically. On the bottom side here, where the atoms are, it's slightly in tension, you have that each atom is at a distance slightly larger than or equal to the equilibrium spacing. And so this energy is stored in what we call lattice strains. Turns out that these strain fields, which is what I've shown here in blue and gray, kind of act like electric or gravitational fields in that they can interact with each other, that is, repel or attract or cancel one another even. And one of the things that, like we can show this example, if you have, let's say, two half-plane edge dislocations where the units on the top are both in compression, those two compression units are not going to want to move towards one another. So the compression units and the tension units are not going to want to move this way, that it's in fact easier for these dislocations to move away from one another. Right? So these are kind of like signs or like charges in electromagnetics. I think you guys are either in Physics 2 now or have taken Physics 2 already. Maybe some of you. How many of you have not taken Physics 2 yet or are not enrolled in it? Okay, everybody's done it. Great. So then the other piece is that strain fields can attract one another, and that's when you have unlike strain combinations, and these can in fact annihilate one another. This is termed dislocation annihilation, that these will in fact be somewhat attracted towards one another, and it doesn't take very much to influence them to move towards one another. And when they line up, when you have a half plane up here and a half plane down here, and they line up together, then you've now canceled out the half plane. You have a perfect crystal again. Okay, so let's talk about deformation mechanisms. The way that a motion of dislocation happens in what we call a slip system. There are a number of directions that the dislocation can propagate, and those directions are all in what we phrase a slip system. The slip system consists of two elements. One is the slip plane. Okay, there's lots of, we've seen looking at different planes inside of unit cells, right? The unit cell system. So there's one particular plane or type of plane in the unit cell on which it's easiest for slippage to occur. And as you might expect, that happens in the plane with the highest planar density. So whichever plane has the most is the most dense, that's the easiest one to slip. Okay? Another thing that helps is that if the planes are not stacked really close to one another, there's large interplanar spacing, right? So that the planes are more free to move past one another. If they're really close to each other, then the interplanar spacing is small, and that's not as easy for things to move in that way. So within the slip plane, there are different directions you could move within a plane, right? Like if I just take any plane in space, like this formed by this sheet of paper I'm holding up right now, there's an infinite number of directions I could move within this plane, right? And then stay within the plane in space, right? So what directions does slip occur. And slip occurs on what we call the slip directions. Those are the directions in which the slip movement is, and they happen with the highest linear densities. So already we can make use of the earlier topics that we talked about in looking at linear density and planar density. Now they both have an application in determining what the slip system is for a given crystal. So let's look at an example. Here's an FCC unit cell. And the most dense plane is the 111 plane. Let's draw that on here. This is the 111 plane. Actually, what it really is it's part of the 111 family of planes. If you'll remember, when we use those curly brackets around the plane indices, that means it's the family of planes, right? Because that plane has a certain linear density, right? But I could draw another plane on here. I'm sorry, planar. That plane has a certain planar density. But I could draw another plane on here that would have the same planar density. Like, what about if I drew the plane going across this way and down? Oops, didn't draw that very well. Hang on here. That's another plane, right, that I just drew in green? It's of the same family though, right? And it's going to have the same planar density. All right, so that family of planes, just to remind ourselves, is the 111 plane. So this is the 111, the 1 minus 1 minus 1, the minus 1 minus 1 1, and the 1 minus 1 1 minus 1. That's the entire. If you were to draw all of the planes that have all the versions within this unit cell that have that same configuration and part of the same family, and then thus have the same planar density, these would be all of them. Now within that plane, let's look at a cross-section of that plane. What direction has the greatest linear density in those in any one of those planes? So let's look over here on the figure B at a face-on view of the plane. What direction has the highest linear density? Like through the center of the triangle, like this? No. The edges, right? Any one of the edges. So these are shown in arrows here already. These edges are the directions that have the greatest linear density. And so they are the slip directions. Yes?
So why is it that the highest planar density or a plane with a higher planar density is more susceptible to slippery? I understand that if there's more space, it's easier to break a bond. But why is it that if it's more dense, it's easier to break a bond?
So the one with the greatest density is going to stay together. The most that has it's the way in that plane can slip and move, and all those atoms being the most dense in that area can stay together and move as a plane.
Well, with most dense, we're looking at the atoms inside, not the outside. So I was focusing on how it affects the bonds outside of the plane. You get what I'm saying?
You mean outside of this triangle?
Yeah.
But those atoms are in the plane, right? Right. This triangle is just the portion of the plane that is inside of the crystal cell. Agreed? Right? The plane, and we've talked about this before, extends forever outside of the unit cell in all directions, right? And so as you look further, we've talked about what the stacking looks like, and this would be one stack in the FCC stack. It would be one of the layers, and all of these can move together because they and they're the most likely to move together because they have they're packed in the most, the tightest, and so the bonds are, it's easiest for these bonds to stay together and these atoms to move as a unit. All right, so those are the linear those are the directions with high linear density, and these directions are, if we were going to draw them on here, this is the 1, 0, minus 1. Right? If I'm going from A to B, I'm going in this direction, right? So I'm going 1 in the X direction, 0 in the Y, and -1 in the Z direction, right? And this one here, A to C, what direction is that? That's, I'm going from A pointing down towards C, right? So I'm moving 1 in the Y direction, 0 in the X direction, and -1 in the Z, right? So this is 0 in the X, plus 1 in the Y, and -1 in the Z. Okay, and then finally the last one, this guy here, what direction is that? If I'm starting at D and I'm moving back towards F, then I'm going what in the X direction? -1. How much in the Y direction? +1, right? And how much in the Z? 0. Right. Good. So those are sets of directions, and they in fact are a family of directions. If you notice that they're, depending on how you look at the unit cell, you know, where you choose your origin or what you call your X and Y and Z axes, these directions are all basically the same. They're moving along the same linear density in there. So they form a family of directions, and that family of directions is the family of directions is the 1, 1, 0 direction. So that's the family of directions. So those are the close packed directions. All right, so how many combinations of possible slip systems or possible slip are there in this crystal cell? There are 4 different planes that could possibly slip, right? And then within each one of those planes, there are 3 possible directions that could go. So the total is the number of slip planes times the number of slip directions. All right, and in this case, a total of 12 slip systems in the FCC cell. Okay. In body-centered cubic and hexagonal close packed, there are other slip systems, and I've shown them here on this slide. So to briefly cover it, and we can kind of recognize that we already covered FCC. We said the slip plane is the 1, 1, 1 family. The slip direction is the 1, -1, 0 family. Okay, that's also part of the 1, 1, 0 family. We've already done that. Let's take a look at the BCC system. let's look at the BCC system. Here, let's draw a plane on here. What's the most dense plane in the BCC crystal cell? This one here, yeah? That has the most atoms per unit area in it. Okay, because the body-centered atom goes right through. It goes right through the body-centered atom. Yeah, and the slip directions on that. What are the densest directions? Well, they're sort of shown on here, right? It would be through the most packed directions, and that's going to go from an atom on the corner through the atom in the middle to the atom on the other corner. Right. So these directions going either way are, and through the center of the plane there, or across the diagonal of the plane, those are the slip directions. So there's kind of there are 6 planes in this is the 110 family, and there are 6 planes. There are 2 possible directions in each one of those planes. So there's a total of 12 slip systems in the BCC. In the HCP, there are, what's the close packed plane? What's the close packed plane in an HCP crystal cell? What does HCP stand for again? Hexagonal close packed. So which layer is the close packed layer? Its name is HCP, right? Hexagonal close packed, right? So which layer is the close packed layer? The hexagonal layer, right? So this layer right here, the one in the hexagon, is the one with the it's the close packed layer. It's the one with the highest planar density. And so that's the only plane that has the highest planar density. So notice that there's not a family of planes in this one. It's just a single plane with the 0001 planar. And so the directions in that plane are along any of the A1, A2, A3 axes. Those are the 3 possible directions, and they're all close packed directions. So those are the directions slip can occur. So there's one plane that slip can occur in. There are 3 directions in that plane, so the number of slip systems is only 3. So what does it mean to have more slip systems or less slip systems? Oh, and I've listed some example materials that are these crystal structures. So for example, BCC is alpha iron, molybdenum, tungsten, and FCC is things like aluminum, copper, gamma iron, nickel. Hexagonal close packed is things like cadmium, magnesium, alpha, titanium, zinc. So what does it mean to have more or less slip systems? If you have more slip systems, there are more options or possibilities for dislocation motion to happen. Right? The higher the number of slip systems, the more pathways there are for atoms to slip. Because those slip systems are the ways that atoms can, in fact, move. Their own motion is only going to occur on those slip systems. There's not going to be motion in any other direction. It's only going to be in those planes and along those directions. So the more planes and directions you have to choose from, or really the total number of slip systems, the higher the chances for plastic motion or plastic deformation. What that means is that the material with more slip systems is more ductile. It can plastically deform better. So let's look at slip in a single crystal. and what happens as we apply a force to a single crystalline material. So here I have a cylindrical specimen with a cross-sectional area A, and we're looking at we've cut it in half, where we're looking at the slip plane, and that slip plane has an area we're going to call A prime. It's not the same area as the cross-sectional area A of the sample, right? Because if you're looking at cross-section through the plane, it cuts through a longer diameter than you're looking at an ellipse plane, right? And the area is larger. What we're going to look at a little bit here are some slip directions and some quantities here. So let me define a few quantities. There is, let's see, how do I want to do this? There is the slip direction, and this is one of the directions in the plane. Right? This is the direction that slip can occur. So the question is then, if I'm pulling with a force F in this direction, vertically upwards in the Z direction, how is that going to influence slip to happen in this direction? Right? It would seem to reason that if I was trying to deform something, the best thing to do would be to take a force and apply it in the slip direction, right? Like parallel to the plane and in the exact direction on the plane with the slip direction. You can't do that because I'm not pulling from the side here. We're pulling from it this way. So how does the application of a force on the ends here resolve to or end up in a way of producing a force in the slip direction? Let's look at the mechanics of it, and let's define some angles here. So there are a couple of angles. One of those angles is lambda, and lambda is the angle in between F and the slip direction. And you see that here, right? This is the angle in between. This is three-dimensional, right? So this is the angle between F and the slip direction in this direction. So we'll see where the F is going to come back here in a second. The other angle we'll define is called phi, and this is the angle in between F and the normal to the plane. The plane normal. The normal to the slip plane. One thing I'll point out is that the normal to the slip plane and the slip direction, what do you think the angle in two-dimensional space is between the normal to the slip plane and the slip direction? But don't try to figure it out from looking at the diagram. Figure it out from thinking about what it must be. So here's the question. What must the angle between the slip direction and the normal to the slip plane be? 90 degrees. 90 degrees, because the slip direction is always only within the plane. The motion can only happen within the plane. So if the direction is somewhere, some vector that's inside of the plane, it has to be a 90-degree angle. So this right here is a 90-degree angle. Okay, they're orthogonal to each other. All right, so that's that piece. So what happens when let's say we're up here, we apply the force F. And that force F is going to break down into components. It's going to resolve to some components. There's going to be a component that is normal to the slip plane, and there's going to be a component that's parallel to the slip plane. And what we're interested in is, let's find out F parallel, which is the components of F that's along the slip plane. Okay, so what is that value? What is F parallel? Help me solve it. So let's draw it in there. What are we talking about? We're talking about this. Oh, that's not going to show up very well. Hang on. What force are we talking about? Let's draw it in red. We're talking about F here. So let's say I'm applying, this is F at this point, right? And I want to know what F parallel is, the force that is parallel to the slip plane, because that's the only way that dislocation is going to occur, is if something does in fact pull in the slip direction. So what's the angle? Well, we can kind of try to draw it on here, right? If I'm going to sort of try to draw this as a 90-degree angle, you see that? Is that all right? Then what's this angle here? Is it 60 degrees? Can we say it's 60 degrees all the time? It is lambda. It is lambda. This is lambda. That's right. This is lambda. So let's draw that again here. So this is lambda. So F parallel is equal to, what's it going to be? F times the cosine of lambda, right? Good. Good. So we've found the parallel force. Now, what's going to happen is that there will be a shear stress in the direction of the plane here, and that shear stress we're going to write as tau sub r. It's what we call the resolved shear stress. And what we can say is that, and this goes the same with shear stress that we've seen before. Shear stress, tau sub r, this is the resolved shear stress. And it's called the shear stress because the force is pushing parallel to the area that the plane of atoms is in, right? And not perpendicular. So even though we're tensile loading this thing, the overall sample, a component of it is in the slip direction within the plane, and that's causing the plane itself to be shear loaded. Does that sound okay? Sound reasonable? So tensile loading at the macro properties of the sample, in fact, resolves to shear loading along the plane. That's how planes slip in the sample. Questions about that? Seems fair enough, right? Reasonable? Okay, so the shear stress happens along that direction, and shear stress, as it was defined earlier in the chapter, is still just equal to the force applied parallel to the area, F parallel, divided by the cross-sectional area of the plane. What's the cross-sectional area of the plane? Is it A? Or is it A prime? It's A prime. It's the ellipse, right? So now what we need to do is find what A prime is. So what does A prime equal? And what we can do is describe this in terms of A. So let's take a look at a side view here. So if I take a look at the side view, here is my sample A, or here's the side length A prime, and the bottom here is A, yeah? And what we said was that the force F was being applied like this. Now, the normal to the plane is in this direction, right? That's the normal to the plane. And I should be drawing vectors on these forces here. Whoops. All right. So the angle between these guys is what? Lambda? What's the angle between F and the normal to the plane? Phi, right? Great. So what's this angle? Also phi. That's right. This is also phi. So if that's phi, how do I relate A prime to A? Oh, and let me actually do it this way. Let's say A. Let's say what A equals. A equals how much of A prime? A prime times cosine of phi. Right? That's okay, right? Yep. So then, therefore, A prime equals A over cosine phi. Now, does that make sense intuitively? Take a look at, should A prime be larger or smaller than A? Larger, right? So when cosine of theta, when phi is 0 degrees, right, which would mean the normal of the plane is directly in line with F, then A prime is equal to A, right? And as phi gets larger and larger, cosine of phi becomes larger than 1 or smaller? Smaller, right? Like it'll go to like 0.75, a half, so on and so forth. So you're dividing by something smaller than 1, so A prime becomes larger. So this is good. We intuitively expect A prime to be larger than A. And that is what's happening. So what we can do is put this all together and just write out that T sub r is equal to, let's put in for F parallel. It's F times cosine of lambda. And then let's put in for A prime. That's A over cosine phi. Or in other words, this is equal to F over A times the cosine of lambda times the cosine of phi. What is F over A? F over the original cross-sectional area. This is the stress, right? So, great. What we've just done is formed a relationship called the critically, or the resolved shear stress, which now relates the applied stress to the sample. So here's our formula. This tells you, this based on the applied stress, a tensile stress to the formula, or to the sample. If you know the angle between the direction of the tensile applied stress and the normal to the slip plane and the angle to the applied stress and the slip direction, you can find what the resolved shear stress is acting at the plane. All right. Where we'll remind ourselves that what phi and lambda are. Okay, so this allows us to basically track what happens at the atomic level in geometry on the atomic level in terms of a plane slipping to applying a tensile stress. Questions? Nick? So that's a good question. I think, did you say if you add phi and lambda together, are they 90 degrees? Good question. And it's a topic of our next slide in a second here. Do you think they'll ever be any smaller than 90 degrees? Oh, sorry. No. Adding them together. Yeah. Will phi and lambda ever be smaller than 90 degrees? No. They're normal to each other. And so if you're, and they're separated also by the force F. So they're normal to each other. The smallest adding them together could possibly be is 90 degrees.
Are they normal to each other, or like the addition makes them normal?
They're normal to they're orthogonal to each other, the slip direction and the slip plane. But adding, but that's not the angles we're talking about. We're talking about the angle between the slip direction and the applied stress, lambda, and the normal to the plane and the applied stress, phi. And so the sum of those two can never be any larger than, can never be any smaller than 90 degrees. And we'll show that in a second. This slide goes through the same derivation that we just did for the critically resolved stress in a slightly different way. Basically says you apply a tensile stress, sigma is equal to the force divided by the cross-sectional area. There's some slip that occurs. We note that the planes slip past one another, and we introduce a normal vector called n sub s, and we introduce that the resolved shear stress is the F sub s over A sub s, the slip plane area. So this is all the same derivations we just did, but doing it much more quickly and with some other colored diagrams. This finally throws in that F sub s in the slip direction is F cosine lambda. A sub s, the slip plane area, is A over cosine phi, just like we derived, and then gives you the formula. So let's look at the critical resolved shear stress. Yeah, actually, you know what? Let's take a quick break, and then we'll look at the critical resolved shear stress in a moment. And so let's break, and we'll come back at let's just say 7:20. You can use the muscle operator. So if you want to get just the digits, like if you have like 1,005, and you want to find this digit, right? You know it's a 4-digit number. What if you just take the number 1,005 and you modulo divide it? Or modulo operator gives you the remainder. You divide it by 1,000, you get 5. Even if you, that's one way to do it. Another way to do it, you can do this too. You can also, let's say you have 1,005. You can try that. But you could also divide this by, let's say, 100. And what are you trying to do? You want to extract digits from each. You want to grab just the digit, right? Yeah. So this would get you just that digit. You got to be careful with the, like if this were not 1,000, so this would be 5, right? This would be equal to 5. If this were 85, then this would be 85, right? So you might actually want to do mod 100. 100 goes into 10,000. That would still give you 85.
So you could do a mod on that though.
Yeah, or you could do mod 10. 10 goes into 1,085 a fixed number of times, okay? And then, yeah, or not a fixed number, it goes into 1080 a fixed number of times, and then there's 5 remainder. So this is what you want to do, is mod 10 to get this digit. Mod 10 will always give you that digit. What if you did, let's see, what if you did, now you take 1085, and can you do mod 100 to get the 8? Not quite, because you need the 8 by itself. So what can you do? What you can do is take it, divide it by, let's see, 10. Is that all right?
You get a 108.5.
You get a 108.5, right? Equals 108.5, but if you do integer division, like the integer 1085 divided by the integer 10, you get 108, right? Yes. Because the 0.5 will drop away, right? Due to type to motion. Okay, and so then you can take that and now mod 10, and you'll get the 8 left over. So this, which you can put it all into one and just do this. And you can kind of grab out the third digit from doing this. Like, so say there was a 4 here or something. You can divide by 100. So if you have like 1485, divide by 100, that gives you 14.85. 14.85, but it's integer division, so this is not there. So then if you do 14 mod 10, you get 4, right? So you can just do all this and do that divided by 100 and then mod 10. And that would give you 4. You can use 4.
So defining charts like for example, and inputs would be charts.
Yeah, there are ways to do that. I mean, are you storing them all into an array or different charts?
Yes.
Yeah, you can use like A to I. Put in the characters, see it returns back a number, which is yeah. And there are other ways to do it too. You can actually just use the ASCII values of the table and find out what it is. Yeah. Sure. Yep. Remembering back to 250. Mm-hmm. Slightly different one, I think.
I remember solving it at the end. It came out to be the same, and I was like, this is wrong.
Yeah.
That was funny.
Yeah. So they're doing a slightly different assignment, but using the same, the modulo operator. Yep. Yeah, that's a good one.
This kind of was that me and including.
Oh, okay, good.
That whole including more.
Good.
You're from the market?
Yeah.
I'll trade for you.
I'm with her too.
Yeah, I'll trade for you.
Oh.
Okay, so let's welcome back, everybody. Let's pick up where we left off. What I want to talk to you about now is the critical resolved shear stress, or tau sub CRSS, the critical resolved shear stress. So as we just mentioned shortly ago, there are many different slip systems, places that slip could occur. So which direction is the slip going to happen in, right? If there are 12 slip systems and in like an FCC crystal, which of those planes and directions is the slip going to occur in? The most favorable one, the one where the likelihood is highest that the slip is going to happen here, is where the critically resolved shear stress is maximum. So how do we find out where it's maximum? Let's take a look. Here we have the critically, or the resolved shear stress, the maximum, is, well, if we're applying, we can also call this TCRSS, by the way, the critically resolved shear stress. It's the same as the maximum resolved shear stress. It's going to be sigma sub y, oops, hang on here, times this cosine phi, cosine lambda. So the stress is already, it's constant, right? So really this is maximum when this term, cosine phi, cosine lambda, is maximum, and this is called the Schmidt factor. Okay, when the Schmidt factor is the highest, then in maximum, that's when the shear resolved stress is maximum. So it has to do entirely with these angles, the angle phi and angle lambda between the normal to the slip plane and the tensile stress, and the slip direction and the tensile stress. Okay, so when are those going to be maximum? We can do a little bit of math to figure this out. So recall that we said that if we're looking at the area and we're applying the stress in this direction, let's just call this N, the normal to the plane here, and let's call this D, the direction that this is going to occur in. Remember that N and D are always 90 degrees, right? So the angle ND is always 90 degrees. Therefore, we've talked about phi is the angle between the normal and the stress, and lambda, which is the angle between the normal and the displacement, or the direction vector. Phi plus lambda, what we can say, is always going to be larger than or equal to 90 degrees. It can't be any smaller than 90 degrees. The only way it could be 90 degrees is if the slip plane was exactly parallel. I'm sorry, the slip plane was exactly perpendicular to the applied stress. In other words, if you applied the stress exactly in the normal direction, then the angle between the stress and the normal would be 0, and lambda would be 90 degrees. Okay, so we know that that's true. Let's find the maximum of cosine phi cosine lambda. And what we'll say is that when this is going to be biggest, because cosine and what's the largest that cosine, that this term could be? Cosine of one quantity times cosine of another quantity. What's the largest that total quantity in the parentheses could ever possibly be? 1. That's right. So let's solve this for when, well, let's just say that this is max when phi plus lambda is equal to 90 degrees. Okay? So then what we're going to say is we've got cosine phi cosine lambda. We're actually going to rearrange this phi plus lambda is equal to 90 degrees. We're going to write that phi is equal to 90 minus lambda. We can do that, right? So we'll put this in here. We'll say cosine of 90 minus lambda is times cosine of lambda. And what's the cosine of 90 minus lambda? It's another way to write that. Sine of lambda, right? Sine of lambda times cosine of lambda. Now we can rewrite this, again, using another trig identity. This is equal to 1/2 times the sine of 2 lambda, double angle identity. Okay? And if we're saying that this is what we're going to call f prime of lambda, this is now a function of lambda, right? We want to find out when f prime is equal to 0. We can actually write this as f prime equals f prime of lambda is equal to cosine of 2 lambda. I'm sorry, this is just f of lambda. F of lambda is 1/2 sine 2 lambda. So f prime of lambda, if we find its derivative and set it equal to 0, because we want to find out when this is maximum, right? So we set this equal to 0, and we find that this is maximum, or I'll write it down here. This is maximum where we get that 2 lambda is equal to 90 degrees, right? Or in other words, this is when lambda is equal to 45 degrees. If lambda is 45 degrees, then phi must be 45 degrees if we're talking about when this is maximum. Phi must be 45 degrees also. So, slip occurs when phi and lambda, the most likely direction, the largest Schmidt factor is when phi and lambda are both 45 degrees. And in that case, slip will occur. So what we can say is that if you calculate the TR sub, basically if you apply a stress that is equal to the critically resolved shear stress divided by cosine of 45 times sine of 45, right? That's when lambda, that's when the term is max. Then if your stress that you apply, the tensile stress you apply, is this large or larger, slip will occur. If it is smaller, slip will not occur. That's when a sample yields, is when you crest and surpass, because you can apply a stress and the sample will stretch elastically, right? It'll deform elastically, and at some point the sample yields. The point at which the sample yields is this point. If you can find the critically resolved shear stress and plug in the cosine phi, cosine lambda with 45 and 45 degrees each. All right, let's look at an example. Let's say we have a single crystal of body-centered cubic iron, oriented such that a tensile stress is applied along the 0, 1, 0 direction. Okay, let's draw a picture of what we have going on here. So here's our system, and we've got our system. Let me draw this larger, actually. Hang on. Let's draw this a little bit bigger. So here's our crystal system, and we know it's body-centered cubic, so there are atoms at all 8 corners, and there's one in the center. And we are applying if this is the x, y, and z directions, we're applying a stress on the 0, 1, 0 direction. What axis is that on? What axis is the stress? On the y-axis, right? So we're applying a tensile stress, sigma, right at that point, or in that direction anyways, right? So say we have a single crystal. We're looking at just one unit cell of this crystal. It could be many unit cells forming a large crystalline material, but it is single crystal. And we now want to compute the resolved shear stress along a 110 plane and in a 111 direction when a tensile stress of 7,500 psi is applied. So let's break this down and draw each one of these a piece at a time here. We're talking about the 110 plane, right? So it intercepts the x-axis at 1 and it intercepts the y-axis at 1, right? So it's the plane across the diagonal of the cubic cell, right? Of the unit cell. Okay, so there's the plane, and the direction we're looking at is in the 111 direction. Okay, so what direction is that? Let's see, 110 plane and in a 111 direction. Yeah, that's the diagonal vector. Yeah, so instead of, hang on here, we're going to look at, we could talk about this as the 111 family of directions. I'm actually going to make this, let's say we're going from here up to this point. That would be in the 111 direction, right? Or it's in the 111 family. It's really in the negative 111 direction, right? Going from one corner all the way across to the other corner Is that okay? We good there?
How do you choose that direction?
So why did I choose this direction? I think there's a typo in my example. One of the reasons. And how did I know that there was a typo? What's the 111 direction look like? The 111 direction is like this, right? From the origin across that plane, right? Or across that to the other point. Is that direction in the plane that I just drew? It is not. It is not in the plane that I just drew, right? It would be if I drew if I drew a different plane of the 110 family of planes. But I drew the 110 plane as I see it here with just as the exact 110 plane, not from the family. If I drew the family that goes from the back z-axis over to this side, if I drew that one, then that'd be okay. But we know we're not using a direction that is not within the plane. Okay, so I had a typo in my example. All right, so that's the there's the plane. So let's draw them on there. Here's the plane. This is the 110 plane, and then here let's draw the direction on there. This is the negative 111 direction. And now we want to know what the resolved shear stress is. Okay. So let's go and find what that is. So recall that the resolved shear stress, let's solve out for A. The resolved shear stress, T sub R, is always equal to the applied stress times the cosine of the angle phi times the cosine of the angle lambda. And we already know the applied shear stress. The applied shear stress is 7,500 psi, because that was given to us in part A of the problem. Okay, what we don't know quite yet are the phi and lambda values yet. So, how do we find phi and lambda? You could use the dot product. You could use the dot product. Let's look at where is phi, and let's sort of redraw the. Remember that what we're talking about is the angle between. Let's draw the stress right here, right? Just move that stress vector so that it's kind of like sharing the same origin as the slip direction vector. Okay, so that's, now help me draw lambda on there. Remember, lambda is the direction between the stress, the applied stress, and the slip direction, right? So what is it? It's this, right? And is it 45 degrees? Kind of looks like it is, but where would the green slip direction vector need to point to make this 45 degrees? To the right. It would have to be within the front face, right? The fact that the vector is pointing to the back side of the cube makes the angle larger than 45 degrees, smaller than 45 degrees, or still 45 degrees? Smaller? Smaller? Still 45? So if I have this, right, and then I start to take, I don't think I can bend my arms that way. Here we go. If I have this, 45 degrees, right? And I start moving back like this. Does the angle increase? Does the angle increase? What about if I get all the way over to here? Is there a larger angle? Look at it this way. Oh boy, this is getting weird. Anyway, what do you think? Do you think it gets smaller? Do you think it stays the same? Or do you think it gets bigger? Smaller? How about what if I kept rotating the direction vector and now it's pointed out like this? Do you think that's still at a 45-degree angle? Do you think that this points that there's a 45-degree angle between the applied stress and a direction vector pointing on the left face? Maybe definitely not, right? It looks like almost more like 90. Maybe not quite, but hard to say, right? So what do we think? Do you think the angle gets larger? Larger. It gets larger when the vector rotates back the other direction. So it's in fact larger. What angle is 45 degrees? Yes, this is 45 degrees, right? The projection in the plane.
Or the blue line and the red line.
Or this one is 45 degrees, right? Right, but what you have to do is keep track of that this is in this direction here, right? And this is in this direction. You see what I'm trying to draw? Let me draw that better. Let me draw that more clearly. So with this, I want to draw perpendicular to this plane, right? So I can look at what's the right triangle here. This angle is 45 degrees. Then I'll draw a perpendicular down to this guy, right? Right? And this angle is 45 degrees. Do you see that? We're viewing this in 3 dimensions, yeah? Okay, so the way that I like to do this is what can we say here? This is, we can say that the tangent, what am I trying to say here? Let's look at this. How long is this piece here? So what am I trying to do here? Oh yes, yeah. Now I remember. Let me draw you another triangle. And there's lots of ways you can do this. I'm just showing you the one way that I have in my notes here. So let's say that I was going to draw this triangle. We're looking for this angle, right? What if I take and draw a triangle between the direction vector will be one side, the green direction vector will be one side. Another side will be along the stress axis, 0, 1, 0, right? And I'm going to draw a right triangle up to the direction vector. Do you see the triangle that I'm drawing at this point here? Okay, it sort of has one face, one edge along the y-axis over here, one edge that is diagonal on this right face up here, and the other edge is on the direction vector itself, right? Okay, great. Now it's the angle in this right triangle that I want to get, right? That angle is lambda. So let's find lambda. What's the side length here? What's the side length along the y-axis part? We could call it 1, or we could call it, let's just call it A, right? To just talk about it in terms of the crystal length here. What's the side length of this side? Root 2A, that's right. Root 2 times A, right? Okay, good. So then what we can say is that lambda equals the tangent of, I'm sorry, this is us trying to find lambda. The tangent of lambda, we can say, is the square root of 2a divided by a, right? It's opposite over adjacent. Is that okay? Right, so the a's are gone, and then what we find is that the tangent of lambda is equal to the square root of 2. And what we find then is that lambda is equal to 54.7 degrees. How about phi? It isn't necessarily 90 minus that. That would be for the critically resolved shear stress, the maximum stress. What is, because phi and lambda have to add to be at least 90 or any larger. What direction is the normal to the plane in? Let's draw the normal to the plane on there. It's in the 110, right? It's like I could draw it up here and it points in this direction, right? That's the normal to the plane. Yeah? So why don't we draw it, instead of there, let's draw it right from that same origin point, and we'll draw it pointing out here. The normal is, the angle right here is between stress and the normal plane is 45 degrees. Now let me actually say that that's 45 degrees. This is phi, which equals 45 degrees. You don't even have to calculate it. You can just look at it from geometry here. All right, so great. So phi is 45 degrees. And then you plug it all in to get your, let's say we put in here, we say that the resolved stress is the stress applied, which is 7,500 psi in this case, times the cosine of phi is 45 degrees, lambda is 54.7 degrees. And what you get is that this is 3,064 roughly psi. All right, let's do part B. So we say if slip occurs on a 110 plane and in a 111 direction, so I think this should still say minus 111 direction. And we've just been told the critical resolved shear stress. They said that's 4,350 psi. Find the yield strength. Remember, the critically resolved shear stress is sigma sub CCRRS, or I'm sorry, not sigma, tau, tau sub max. It's the maximum shield stress that, or shear stress that needs to be applied to get slip to occur. And once slip occurs, the sample has yielded. So if we know the shear stress, we can find what the yield strength is. All right, so then we jump back here to just basically say that our tau CCRS is equal to 4,350 psi. What's the yield strength? And we can pretty much use our maximum. We can use the fact that TCCRS is equal to the yield strength, sigma sub y, times the cosine of phi times the cosine of lambda. Now phi and lambda in this case are still the same angles. They're not 45 and 45. I want to clear that up. That might have been confusing from what we were saying a moment ago. Because we're saying if slip occurs on a 110 plane and in a 111 direction, then we're saying slip occurred in that direction, then and we're applying the load or the stress, the tensile stress, on the y-axis, then the angles of phi and lambda are still the same. All right, and so what we'll do is then, question?
Yeah, so what is it that if they are 45? Or
so the way to calculate the critically resolved shear stress is to assume that they are both 45. Right. So unless they're given already. If you have actual planes and directions, then you have actual phis and lambdas, and those are the ones you work with. All right. So we basically take the apply 4350 psi and divide that by the cosine of phi, which is 45 degrees, times the cosine of lambda, which is 54.7 degrees. And what we find is that the yield strength is 10,600 psi. Right, so that was kind of a lengthy example, but one that's really good to go through because you're going to be doing some of the same stuff and going to need to analyze the geometry of this kind of thing with the angles between the applied stress and the slip directions. All right, here's another example. Let's say we have a single crystal. Here we're applying 45, take a look at purple, the purple box at the bottom, we're applying 45 megapascals of tensile stress, and we're saying that we're given the angles phi and lambda, or 60 degrees and 35 degrees respectively, and we're first asked, and we're also given the critically resolved shear stress, 20.7 megapascals. And the first question we're asked is, A, will the single crystal yield and actually plastically deform? And B, if it won't, what stress do you actually need to get it to plastically deform? In other words, yield. So the first bit is you just plug this in plug in lambda and phi, and the fact that the applied stress is 45 megapascals. And what you find is that the resolved shear stress, tau, is 18.4 megapascals. Okay, that's how much stress is going to be applied to the plane in the slip plane on the slip direction. That is less than the critically resolved shear strength, 20.7 megapascals. So the sample will not yield. Does not cause, so an applied stress of 45 megapascals isn't large enough to cause the crystal to yield. All right, so part B to this, well then how much stress would we have to apply to get it to yield? Another way to ask the same question is, what is the yield stress? This is really asking what is the yield stress. If you're asking how much tensile stress you have to apply to get the sample to yield, it's the same thing as asking what is the yield stress. All right, so basically work backwards. You're given phi and lambda. The Schmidt factor is 0.41 by calculating those out, right? Cosine phi times cosine lambda gives you this is the Schmidt factor. and then you're going to solve for sigma sub y. You just plug in the critically resolved shear stress, divide it by the Schmidt factor, and you have that it would take 50.5 megapascals to get the sample to yield. So what you can say is that for deformation to occur, the applied stress must be larger than or equal to the yield stress, 50.5 megapascals. All right. So that was for single crystals. How about slip motion in polycrystalline materials? That is, those that have more than one crystal grain in a sample. Turns out that polycrystals are in fact stronger than single crystals. And the reason is because of their grain boundaries. Those grain boundaries are barriers to dislocation motion. If a dislocation is propagating through a crystal, and so let's say I'm a dislocation, and I am, where am I? Where do I want to be? What color do I want to be too? Let's say that I am a dislocation and I'm an extra half plane of atoms moving in this direction. Here I am and I'm moving in this direction. And so, or we could do a different one. We could say that here I am and I'm moving in this direction. And once I get and I encounter the grain boundary right here, the grains in the next crystal cell over are not aligned with the dislocation and the plane of atoms in the grain I'm currently in. Like a really good example of that is like, what if I'm a dislocation? Here's another grain boundary, right? What if I'm a dislocation here? Here I am, and I'm moving in this direction. That sort of shows up. Doesn't show up that great actually. Sorry. How about orange? Is that better? Is orange better? Not a whole lot. But anyway, I'm moving towards the red boundary, right? Well, the next crystal grains are not aligned along that direction. They're aligned on a totally different direction. They're aligned on, they have a totally different alignment, right? So the dislocation isn't going to further propagate to the next crystal grain. Another way to say that is that the slip planes and directions, lambda and phi, change from one grain to another. We also can say that the resolved stress will vary from one grain to another. And that being the case, the grain with the largest resolved stress is the one that yields first. So whichever grain somehow has the largest applied stress to it, that's going to yield before any of the other ones, right? You can think about if you're applying each, we're showing that the tensile stress is applied on the sample. Each of the resolved stresses are going to have different, in each of the grains are going to have different magnitudes because of which one is going to be aligned most with the applied stress. It all depends on the component, the projection of that stress onto the shear plane or the slip plane. And so the one with the greatest resolved stress is going to slip first, of course. We're now going to talk about this as a mechanism for strengthening materials. Doesn't mean that polycrystalline materials are not a bad thing. In fact, if a grain boundary makes a material stronger, hey, let's make some more grain boundaries, right? We can increase the strength of a raw material. Instead of having it be perfectly crystalline, let's increase some grain, or let's create some grain boundaries. So we've already said that these grain boundaries are barriers to slip. So if we were looking at a slip plane and this extra half plane of atoms kind of moving towards the grain boundary, we're going to see that it's going to meet a dead end at the grain boundary. the strength of the barrier is larger the larger the angle of misorientation is. So this angle here, this angle at this point right here, is being larger makes the barrier sort of stronger. And if you have a smaller grain size, there are more barriers to the slip, because slip only occurs within a grain. It's sort of terminated at the boundary of the grain. All right? It's like, imagine if you weren't allowed to go to another state for some reason. You could only move around in California. Then, you know, your motion ends at the border of California. You can't go any further. Right? So same kind of thing. If you have much smaller grains, there are many more barriers to slip. There are many more borders. You can calculate the yield strength for a polycrystalline material. So if you have the yield strength for a polycrystal, this is sigma sub naught is the yield strength for a uniform single crystal. And D is roughly the grain size, and K is a constant based on the material. This is called the Hall-Petch equation, which does the best job it can to approximate what the yield strength is of a polycrystalline material which has a raw material of single crystal yield strength of sigma naught and a grain size of D, an average grain size of D. All right, so how can we, so this is one way to reduce, or one way to strengthen a material is to make the grain smaller. And we'll talk about ways that you can do that. The second one is to form a solid solution. The impurity atoms distort the lattice and generate lattice strains. So the solid solution with the impurities, the minor atoms, they in fact create extra strain. Okay, so a small substitution impurity generates local stress at that point A, and it opposes the dislocation. It acts like a barrier for the dislocation to move. The second piece is that a larger substitutional impurity generates local stress at C and D, and it opposes dislocation motion to the right. So solid solutions, adding impurity atoms into the crystal lattice, further impedes or prevents the motion of dislocations. Okay, this is one of the ways that steel is made stronger by adding carbon into it. Iron is made stronger by adding more carbon into it, which is one of the basics of steels. We talked about lattice strains around dislocations already. You can strengthen a solid by solution alloying. Small impurities, that is the minority atoms that are smaller than the host atoms, tend to concentrate at the dislocations and in the regions of compressive strains. And that partially cancels the compressive strain. The larger impurities tend to concentrate at the tensile strain regions in a dislocation, and they continue to oppose, or also oppose, some of the lattice strains. Here's an example in strengthening copper by adding nickel into it. And so the tensile strength and the yield strength in megapascals of copper are shown here in both these figures as you increase the concentration of nickel from 0 up to 50%. This is showing you what the yield strength and tensile strength, how they change. So we're seeing a direct effect of solutioning or strengthening through solid solution. A third strategy is precipitation strengthening. And this is through putting hard precipitates inside of materials. And they act as major barriers towards slip. One example is embedding ceramics into metals, like silica carbide in iron or aluminum. When you do that, this creates a much stronger material and a couple of applications of precipitation strengthening. One is ballistic vests, the trauma plates in ballistic vests, which can stop bullets. Okay, and those are actually done with silica carbide, used in composite armor and ceramic plates or discs. Another one is in strengthening the wing in an airplane. Aluminum is strengthened by precipitates formed in alloying the metal. The final one is through strain hardening, and this is called cold work, meaning that it's work where the sample is deformed at temperatures below the melting point of the. It's when the sample is worked at room temperatures, basically, for most metals. And here's some common areas to reduce the cross-sectional area. We call this cold work. We measure it in a percentage, and we measure it by how much the area of the sample has reduced in percent from its original area. So you take the area A0 minus the new cold worked area divided by A0 and multiply it times 100%. That gives you a percentage of how much the area has decreased. Here are 4 ways to decrease the area of the sample. One is called forging. And in that you have a die that has a cutout of a mold that you want your sample to mold to. And you push and force that sample, you force the die around the sample and Hello? All right. Hopefully we're back online, and I'm going to do my best to stand in front of my computer. For those of you watching at home, my in-ear microphone, the battery died. And so glad to hear that you can still hear me a little bit. So to pick up where we left off, we were talking about forging, or we were talking about strain hardening, and this is termed cold work. And one of the ways of doing that is by forging a material. And that is through compressing a die around a blank specimen and changing its area. Another mechanism is, or another technique is called drawing a material. In this way you have 2 die that are cutting edges. They can cut through. They're really hard materials, and they can cut through, let's say, the metal that you're pushing through them. And you pull the material through the 2 dies with a tensile force, and the final area, A sub B, is less, it's decreased. Another one is rolling. I'm actually doing this in the lab here this semester. We have a rolling press in the back of the lab, and in this way you roll the sample through a couple of 2 roller bars, and you decrease its area. Over time, this is a way of cold working a material. Another one is through extrusion. It's kind of similar to drawing, but the die are slightly different shapes, and you're pushing the material through rather than pulling. Okay, all of these are methods of cold working a material. What does that do to a sample? If you take a look at a material, let's look at low carbon steel. If it has not been cold worked at all,
its stress strain curve is shown in green. That's 0% cold work. Contrast that with adding 4% cold work. You've reduced the area by 4%. Now its yield strength and tensile strength its yield strength is significantly higher actually, and its tensile strength is a little higher. Contrast that with reducing the area by 24%. The yield strength and tensile strength are much, much higher. So you can see the yield strength increasing in each one of these samples. You can see the tensile strength increasing each time through the different amounts of cold work. You can see the ductility, in fact, decreasing as you cold work the sample, right? The more you cold work it, the less ductile it is. Okay, and that makes some sense because as you're cold working the material, you're moving dislocations around, and you may in fact be changing the number of possible slip points. So this is another slide that says pretty much the same thing. A ductile metal becomes harder and stronger when it's plastically deformed, and plastic deformation increases dislocation density. When you reduce the area, you're making the number of dislocations greater per unit volume. So also makes it more difficult to move the dislocations. And this is that same graph we just saw shown in a three-dimensional view of stress versus strain, and a third axis of percent cold work shown. You can see the stress strain curves changing. Okay. What are some mechanical property alterations due to cold working? Let's take a look at the values of the yield strength, tensile strength, and ductility after cold working this sample of copper. So the sample has an original diameter of 15.2 millimeters. We cold work the copper and reduce its final diameter to 12.2 millimeters. So how much cold work have we done? Well, it's the initial area minus the final area, the cold work area, divided by the initial area, times 100%. And since pi over 4 cancels out all of this, you can actually look at it in terms of just the differences in the squares of the diameters. And when you put that in, you find out that the cold work was 35.6%. So how do we find out what the yield strength, tensile strength, and ductility are after cold working copper? Luckily, it's been tabulated already, and you can use some graphs to find out. So these are three graphs of the yield strength in megapascals, tensile strength in megapascals, and ductility in percent elongation, all versus cold work, respectively. Okay, so if we had 35% cold work, you trace that on the graph, or 35.6% cold work, we see that the yield strength of this copper is now 300 megapascals. At 35.6% cold work, we're finding the tensile strength is now 340 megapascals. And at 35% cold work, we see that the ductility of this copper has reduced pretty dramatically down to only 7% elongation. So you can only elongate it 7% before the sample is going to snap. That's what the ductility means. Initially, you could elongate that copper 40% before it would snap, before you did any cold work. And now, you've really increased the strength, but also at a cost of losing ductility. But that's okay. You might not need a ductile sample. Your application might be only focused on stress, on the strengths, yield strength and tensile strength. So what happens if we cold work a material and then start to heat it back up? What do you think will happen? Turns out there's a process that occurs. And the process is three parts. After you cold work a material, you've pushed dislocations closer and closer together. You've made grain sizes smaller, in effect. A 1 hour heat treatment at the annealing temperature, and this is for a particular metal. I'm sorry, these are annealing temperatures. These are processing temperatures you can apply to any metal. Decreases the tensile strength and increases the percent elongation. So you can in fact recover how you've processed the material. You can cold work a material and change its tensile strength and its ductility, and then put it into an oven or a furnace and warm it back up and hold it at a fixed temperature for a while, and increase its ductility again and decrease its ductility. The question was, does the ductility, or does the material recover its original percent ductility? And the answer is yes, nearly. If it was a pure sample before, like a nearly single crystalline material before, it should have roughly the same 5% ductility, or the ductility. So what happens is the effects of the cold work are nullified. The sample returns to its original state. If it was, well, we'll look at what happens with the number of crystals. So here's a graph of tensile strength and ductility versus the annealing temperature. And you'll see three phases here. One of the phases is what's called recovery. This is where the sample, well, we'll see in a second here on the next slide. The next phase is recrystallization, and this is where crystal grains form, and then they grow at a given temperature. And I'll show you slides of each of those now. So in recovery, at higher temperatures, some of the stored strain energy, we talked about there being energy stored in the strains, is recovered by enhanced atomic diffusion. What is enhanced atomic diffusion? What is this? What's atomic diffusion again? What's atomic diffusion? Motion of atoms, right? Just atoms moving around. They diffuse through a material. That's atom movement, right? So atomic diffusion is the motion of atoms. Why is it enhanced? Heat, because we're heated the sample. Great. So at elevated temperatures, some of the stored strain energy is in fact recovered by enhanced atomic diffusion because it's warmer. This reduces the number of dislocations. All right? What's the driving force in that? It's the reduction in strain energy. The second phase, in recrystallization. This is the formation of a new set of grains that are strain-free with low dislocation densities. These are near pure crystalline grains. When you heat the temperature, and it's not melting point, you're just warming it up. Atoms can shift around and form new neighbor bonds and move and shift into a good, perfect crystal again. Okay, and so what drives that? The difference in internal energy between the strained and unstrained material. It's sort of like a spreading of an equalizing of energy. We're moving everything back to equilibrium spacing and the lowest energy form that you can get to. The recrystallization temperature happens at is the temperature at which recrystallization is completed in 1 hour. And I believe we usually refer to this as T sub R. It's the recrystallization temperature. The higher the cold work, the more cold work that's done on a material, the larger the driving force and the lower the crystallization temperature. So as the percent cold work goes up, the recrystallization temperature goes down. It takes less heat to get things to recrystallize because there's a greater desire for the energy to equalize. There's a large imbalance in strain energy. Okay, so let's look at, here's a scenario. So you have a reduction of dislocation density by annihilation. The extra half planes of atoms near each other, atoms diffuse to the regions of tension, and the dislocations annihilate and form a perfect atomic plane. Another scenario is that there's an obstacle dislocation. The gray atoms leave through vacancy diffusion, allowing the dislocation to, quote, climb or move in that direction. And the climb dislocation can now propagate and move on a new slip plane. And the opposite dislocations can meet and annihilate. All right, so that's one mechanism of those were two mechanisms of this recrystallization. I'm sorry, of grain, of recrystallization. So new grains are formed in the sample. So what we're looking at in the micrograph on the left is brass that has been cold worked 33%. And you can see very elongated grains, right? This might have been cold rolled. And so the grains on here are, notice that they're really stretched out, right? Those are big, long, wide grains. At only 3 seconds in a 580 degrees furnace, notice that what you see on here are a bunch of small nuclei, new crystals that have nucleated. These are atoms or molecules in a sample that have repositioned themselves and formed a new crystal structure. They consume and replace the parent cold work grains. So once the crystals are born, they sort of use the same material as their parent grain, and then they grow. And so after 4 seconds in that 580 degrees C oven, the cold work grains are consumed by the nuclei, and you can see the grains growing. After only 8 seconds, you can see the grains have actually now grown and run into each other. All right, and as they continue to grow, even after 15 minutes, you can see that the grains have grown to pretty large sizes. The small grains don't survive. They're usually pushed out by the larger grains, and the bigger grains continue to grow. The longer time you anneal a sample for, that is hold it at a fixed temperature, the larger the average grain size in the sample is. You can relate this to the grain diameter at a time t. You can relate to the original sample's grain diameter and the elapsed time at a particular temperature. So if you were to look at this graph again with the annealing temperature increasing, we can see a sort of pictogram of the cold worked and recovered grains forming. And the longer you hold the temperature for, or the higher you hold the temperature, the larger the grains are going to be. The larger the new, the recovered cold worked. The cold worked and recovered grains are going to be larger the higher the temperature, the annealing temperature is. All right, that concludes our discussion on Chapter 7. Like I said, there will be a homework assignment posted tonight or tomorrow morning for you guys to work on. I'll be doing about a week. Go. Great. Well then with that, I will see you all in lab on Thursday. See you then.